leave it up to me. So not to worry too much about calculations. There are some basic ones that you can calculate with no problem. But when there is something that you think it is not possible for you to do that by limited time you have, just leave it alone. I'm not going to subtract too much points for calculations. Anyway, so let me first then go over this material. I believe I sent this material to all of you last night. Some people, they said that I forgot to send the solution to homework number 2. And I did that, and I apologize. I assumed that I did it somehow because I sent the solution to homework number 3 as well. So I hope that you have everything that you need in your hand. Let me get the confirmation from either Julia or Kennedy or Fang. Somebody tell me that you have everything that you need in Canvas. Did you receive this material, Kennedy or Julia?
Yeah, I see everything on Canvas.
Very good. Excellent. So that's a confirmation that you have everything. So this material obviously follows after I finish the mathematical background based on vector spaces and linear operator. You have that lecture notes on that material related to vector spaces and linear operator, matrix representation of linear operator. I talked about that one in the class, and I sent you the material, my lecture notes. So, and you also solved some homework problems related to that. Then when we started with the textbook that you have, we started with chapter 3, which is mathematical representation and so forth, mathematical representation of the system, modeling, mathematical description of the system. And I'm starting from there, chapter 3. Then I go back to chapter 2. And then I talk about chapter 4, which is the response analysis. And then something related to realization. And I covered that one for both linear time invariant case and linear time varying case. Okay, maybe this is not exactly the same order as you have in your textbook, but these are the material that we covered. So let us see what we have here. Remember, I talked about mathematical representation of linear dynamical system, and there are 2 representations that we divided based on the differential equation. One is called input-output description, and the other one is state variable description. Why we do that is because of convenience. When you take a linear system course, linear system theory and mathematical representation of system, it is convenient to deal with these 2 representations. Although differential equations are important, but then for the sake of modeling and analysis of a system, it is convenient to work with these 2 representations. The input-output description for the linear time invariant systems looks like this. And as you remember, this G is called the impulse response. We derived this equation for you for the linear time invariant causal system with the initial relaxed system at t0 equal to 0. You can write it this way. This is the input-output description. Then the state variable description looks like this. X dot equal ax plus bu, y equals cx plus du. Now, for the linear time invariant case, you can have a lot of flexibility to deal with these 2 systems. But for linear time varying case, you don't have too much flexibility other than dealing with the time domain representation. Later on, you will see that these equations can be written into the Laplace domain very conveniently, whereas here you're dealing with the time varying system, and only you can use this 2 representation and try to find out exactly what happens in analysis and design. For both of these situations, we can represent the input-output description with this block. And here also a block, but we are taking the internal variables of the system, which are called the X That is the minimum amount of information that together with initial condition and input, you can completely characterize the system, whether it is time invariant or time varying system. So this is just the two representation of dynamical system. As far as the input-output description is concerned, you have what it means basically is the following, that if you apply an impulse here, then the response here, G of t, becomes the impulse response. It's called the impulse response. If you have an arbitrary input, then this U that you consider as delta, to get the impulse response here, you get for any input U with the impulse response that you have, you can find the output response of any input. So remember, here I have two signals, one impulse, the other one arbitrary input. If you have an impulse, then you have G of t, which is called impulse response, which is this quantity. Now, if you have an arbitrary input, then you can substitute that arbitrary input here, the impulse response, if it is given, then you can find the output response. This is when we go to the output response, we will talk about this equation again. Now, for the state variable representation, we showed that how you can obtain the state variable from a differential equations, a state equation from the differential equation. So if you have an nth order differential equation, you can represent it as a set of n first order differential equations, which is called the state equation. Here I showed you a second order differential equation where you can consider this system to be either electrical or mechanical, it doesn't matter, but you can define y equal x1, y dot equal x1 dot equal x2, y double dot becomes x2 dot, which is the highest order derivative here. It can be written as a linear combination of the other two state variables, and this is the way that you write it in the vector matrix notation. Already you know about this, but I'm just this is a summary. I'm going to talk about that one very briefly. So here, as you can see, I put one mechanical system to have some sort of a physical intuition, a mechanical system. As you can see, I wrote here writing a state equation for the simple mechanical system. And here you have some sort of a feeling what those state variables are defined. For this system, the displacement y equal x1 is considered as one of the state variable. The velocity, which is the derivative of displacement, is the second state variable. And the highest order derivative here can be derived in terms of this x1 and x2 that you define. And you have the state equation in terms of this physical system, which you have some sort of a feel for what are the state variables. Then I spent some time to show you my method of dealing with the circuits. I put on the notes that I sent you, the background information was the graph theory, which I summarized it here with one picture that of how to define the fundamental loops and fundamental cut sets. And through this simple example, I showed you how to obtain the state equation, and you can write the state equation for the circuit. As you can see here, I showed it how to derive based on the simple equation of current voltage relationship between the elements of the system. So, and then you have two fundamental loops, three cut set, two of them can be used. The rest, this one cannot be used. It doesn't give you any information. So basically, if you look at this, that is a good summary of what you learned about writing the state equation for a simple electrical circuit. In the homework that I sent you regarding this, you had the opportunity to deal with some variations of electrical circuits. In particular, when you have, for example, capacitor, there is all capacitor loops. You can put one of the capacitor in a link. You are allowed to do that because one of the capacitor voltage can be written in terms of the other two. So if there is a constraint of of the circuit, you can choose the tree in some ways that basically you reach all the nodes, but you don't generate any loop. But in case you have all capacitor loops, then it is okay to put it in a link. And the resistor are optional in order to reach all the points that you need. So, and the same thing happens if you have all inductor cuts it. If you have one inductor here, one inductor here, one inductor, okay? So make sure that you have the constraint equation between either current or voltages that you can write. Now, once I defined the input-output description, I mentioned that you can, and the state variable description, then I said that you can actually connect the two very easily. For example, if you have a transfer function representation from differential equations, you can have the same equation that I showed you before. You take it into the Laplace domain and then find out the input-output representation in terms of transfer function, as you can see here. For transfer function calculation from differential equation, you usually assume that the initial condition are equal to 0 in order to develop the transfer function. Then the transfer function representation from a state equation. Here you have the state equation. You again, you have to make the assumption that the initial condition equal to 0. So when you take the Laplace transform of this vector matrix equation, you will get this equation, and then you find x of s. The second equation gives you y of s. So when you substitute x of s here, you find out the relationship between input and output, which is the transfer function here. So if I give you a, b, c, d, you can immediately find the transfer function g of s. Now the realization problem is an important problem as well. As you can see here, the realization, maybe I can put this one down below. Okay. So for the realization problem, we have to define it in the following fashion, that when I give you a state equation, you can find the transfer function, and this process is called unique process, because once you have the state equation, the formula that I just showed you defines exactly ABC, based on ABCD, you can find one transfer function. However, if you have a transfer function and you want to write the state equation, this process is not unique, and it's called realization. There are many different ways that you can find state space realization from a transfer function. Here is one example, is a fourth order system, which is represented in this fashion. Now, since the polynomial of numerator and denominator are equal, you can divide to get some sort of a constant term, and that constant term defines the d term that I defined in ABCD matrices. The rest of them here becomes a strictly proper transfer function. And for that strictly proper transfer function, you have one state space realization, which looks like this, which is called controllable canonical form. The way that you can realize this is very similar to that first example that I showed you for the second order system. You can write, based on this transfer function, you can write the differential equation and define your state variable. But this controllable canonical form realization is not the only one. You can have other type of controllable canonical form realization. For example, if you put this A1, A2, A3, A4 in the reverse order on the top here and write 0, 1, 1, and so on, and then 1 comes here, that becomes an upper companion matrix. And the state space representation is still a controllable canonical form. I think here I showed you a procedure for constructing controllable canonical form. Here is a simple example that you have polynomial equal in the numerator and denominator. First, you divide to find out that d term. Then you exclude this one for the rest of the calculation of ABC. So ABC from this part of transfer functions or direct form g of s as can be obtained as follows. So you can find, I explained it here, that this can be considered a new variable, and then you can have this equation can be divided in two parts. and then you can write based on this equation, the differential equation. And then after that, once you have this, then you can also find the output equation from here and substitute the state variable that you define, and you get the controllable canonical form of this transfer function. Okay. Here is another example that we have. I mentioned to you that you have variations of this system. For example, if you have s plus 2 over s squared plus 7s plus 12, you can have the controllable canonical form in this format. So 2 and 1 in the reverse order appear here. And then you have minus 12 and minus 7 in the reverse order here. So this is one way of representing controllable canonical form. If you want to use the representation in your textbook, that is an alternative way of writing it. But since here you can see that minus 7 and minus 12 comes directly from this coefficients on the top, and then you can write the rest of them. The same thing with the 2, 1 will be in the reverse order, 1 and 2, 1 and 2. You can just put it into that representation. It's up to you how you want to represent the controllable canonical form. For the observable canonical form, you have basically, if you transpose this equation here, if you transpose this one, that becomes the A matrix. And then you transpose this one and put it for the B, and transpose this one and define it for C. So this is the observable canonical form. Now, this concept of controllable canonical form and observable canonical form, the word controllable and observability will be discussed later. But people defined it ahead of time. This concept of controllability and observability attached to this state space realization, which will be clear for you when we go and talk about, justification or why they call it controllable canonical form. Will be clear when we talk about controllability and observability later. But right now, you just put that controllable canonical form, observable canonical form, and there is another one which is called the modal form. So the modal form is really a diagonal or Jordan canonical form realization. So that means if you have a transfer function like that, which we did it for the controllable canonical form and observable canonical form, we can do the partial fraction expansion and define the state variable clearly here. And then you define two equations here, write the differential equation corresponding to this, differential equation corresponding to this, and combine these two into the state equation. This representation has a matrix A that is in a diagonal form, but then you have 1 and 1 minus 1 and 2 that are appearing because of those constant terms that we have in the transfer function. So, but the matrix A itself is a diagonal form. So the system is called the modal form, or diagonal or Jordan canonical form realization. Sometimes it happens that when the eigenvalues are complex conjugate, like this example here, there is a transformation, because this is not going to be a physically realizable system. You cannot build analog circuitry to implement this equation with the complex. Therefore, there is a transformation which is called equivalent transformation that transforms this system to a form that it is physically realizable. So that transformation matrix is P equal that and P inverse like this. So if you apply the PAP inverse, you can get that. So I went a little bit ahead of time here because we talk about equivalent transformation after this, but at this point, it is okay to tell you that you can find equivalent transformation to find the physically realizable system. Here is a generalization to a block form, which I'm not going to talk about that one. I'm not going to give you examples that are so, it's going to be time consuming, but I'm not going to give you high order system. Here is exactly those relationships that I just applied for transformation of one state variable to another state variable. And these are the state variable equations, the state equations. you can relate the two state variable by non-singular matrix P, and then PAP inverse becomes A bar, B bar becomes P times B, C bar becomes CP, and I gave you the derivation here once more, and I derived that one during the class a while ago. So in order to show, well, here I have to emphasize that the transformation matrix that you see here in this equation, this transformation matrix P that you see here, is a general relationship that establishes the general relationship between A and A bar without specifying the P. Now, there are certain P that transfer a system to, let's say, controllable canonical form. There are certain matrices P that transform the system to observable canonical form. There are certain transformation matrices that transform the system to modal form. Now, for the transformation matrix that requires to transform a system to the matrix A to A bar, B bar, C bar into the controllable canonical form can be defined after we talk about controllability concept. So I cannot cover it right now how this P looks like. The only one that basically is qualified to talk about at this point is when you transform the system to modal form. In that case, you know that the Q matrix, which is P inverse, is going to be the eigenvectors. So here I showed you that this equation of transformation can be applied to this system up there, which can transfer this one to the modal form. So you find the eigenvalues and eigenvectors. The transformation matrix can be defined by the eigenvectors. Here you see that since we already talked about the mathematical background, this is the only one that you can transform the system to a modal form by this Q matrix. So when you apply the Q matrix with the inverse of the Q, which is P, then PAP inverse becomes a diagonal form here, and 1 minus 1, 1, 1 here. Okay. After that, we went to the concept of response analysis of linear time invariant system first. And I mentioned that again, when you have input-output description like that, in order to find the response, I already talked about that. Given any input here and the given an impulse response, then you can find the output in the time domain. This is sort of inconvenient if you want to integrate the product of these two. So one convenient way is that you can take this system input-output representation into the Laplace domain, and then you get this G of S. In that case, then U is given in the time domain. You can transfer it to the Laplace domain. G impulse response is given in time domain. You can put it in the Laplace domain. The product can be the output in the Laplace domain. Once you have that, you can find Y of t. Okay. So note that the G of t in the time domain gives you the transfer function. So the Laplace transform of the impulse response is the transfer function. So once you have the U, once you have the Y, you can find Y of S. Once you have Y of S, you can find Y of t. Although you can use this integral expression to find Y of t if U and G are given. Here I give you two examples to see how this is done. If I have the impulse response e to the power minus c given, then you can find the transfer function 1 over s plus 1. If U of t is equal to 1, you have 1 over s. There are two options you have. Either you can directly use this e to the power minus t, substitute that equation in the time domain directly, integrate, and get 1 minus e to the power minus t. Or you can use this Laplace expression of the transfer function, input-output representation, and then with the partial fraction expansion and find directly the Y of t, which is the inverse Laplace transform of these two terms, which you get the same result. So once you have that, then we find the second part is the response analysis of linear time invariant system. For that case, you have state equation in this format, we have two responses. One is called the zero input response. The other one is zero state response. I'm not going to go over how I derived the state response x of t. You can actually look at it from here. There's a derivation that I put for you here. So once you find x of t, you will get e to the power at times x of 0 plus this integral. This part is called zero input response. This one is called zero state response. Once you find x of t, you substitute here, you get the output response the same way. Zero input response, zero state response, but with respect to the output. Here, the two are with respect to this thing. Okay. The most important quantity here in order to obtain the response is this e to the power 8. It's called the state transition matrix because it makes it possible to transfer the state x of 0 to x of t at any later time t. So this e to the power 8t should be computed in order to find the x of t. Why? Because once e to the power 8t is obtained, the input is given, the initial condition is given, you replace t by t minus tau, you integrate, multiply the whole thing, integrate, and then add it with this term, you get the general response for the system. So the most important thing is to compute e to the power 8t. And there are several ways that you can do that using your mathematical background of chapter 3 on Cayley-Hamilton theorem, or you can find the inverse Laplace transform of Si minus A inverse, which I already showed you showed it in the next page. The method of e to the power 80 can be obtained in this fashion, or you can use based on the Cayley-Hamilton theorem. I just put the two convenient way to do that. Okay. There is a third method that you can find A into the diagonal form, and then once you have e to the power a hat t, you can go back and find the e to the power a t. That's another way to do it. Here I give you a complete example. I do not want to go over it at all. I just showed you how to obtain general response of the system. You can go and look at it yourself. And this is the continuation of the example. Then a response analysis of linear time varying system, as I mentioned to you, you can only use this equation. You cannot do any transformation to the Laplace because of time varying system that you're dealing with. So here, when U is given, G is given, you can find Y. For linear time varying system, when it is represented by state equation, you have the same terms obtained as zero input response and zero state response. As you can see, this phi of tt0 that was e to the power at in the linear time invariant case. Here, phi of tt0 can be obtained only by one. There are actually two methods also, but one method that I described is based on the fundamental matrix and so on. So this phi of t is called state transition matrix. And then I showed you some theorems about and definitions of fundamental matrix. Okay, so I talked about the fundamental matrix and also the state transition matrix and the theoretical background of that. And then the best way to do it is that one thing that we noticed that fundamental matrix is not unique, but the state transition matrix is unique, obviously should be unique because you want to find the solution properly. You need something that provides uniqueness, and that is the phi. And then I give you some properties of state transition matrix. I give you an example here in the notes. I purposely here cross the T0 that you have option not to solve the problem with T0 if you like to. You can start with the T0 equal to 0 in order to generate the fundamental matrices. I showed that in two different ways when you find the linear independent vectors for initial condition to find the fundamental matrix. And then after that, when you multiply the two, you can get multiply one times inverse of the other one, you get the state transition matrix. This is when we considered 1, 0, 0, 1. But if you use any two linearly independent vectors, like this one here, I put similar to the City Chen, your textbook, where I put x1 of 0 equal 1, x2 0 equal to 0, the other one x1 of 0 equal 1, x2 0 equal to 2. You see that the fundamental matrix was not the same as the state transition matrix. So while this one is not unique, this one is unique. And obviously you can find the solution at the end. I think an alternative solution I also introduced where you consider the commutative properties. Once the commutative properties is valid, then you can find the state transition matrix in one shot like that. So that example that I showed you before can also be obtained using this expression. That will reduce to a function of a matrix where you can use the knowledge of Cayley-Hamilton theorem to obtain the same phi of T0 that we obtained before. So that is the end of the material that I sent to you. I hope it is useful and you can benefit from it. Now, I'm going to talk about the exam, what you should expect to have in the exam. Again, I'm going to talk about that. I have to spend some time tomorrow to put the questions together. So the very first problem that you have, let me see whether I can find some pen like this. So problem 1 is related to vector spaces and linear operator. It consists of two parts. One is vector space and linear operator. And then there is something related to matrix analysis. Matrix analysis, like algebraic equations, something related to that. Because if you remember, we said that the linear operator can be represented by a matrix A, and then we talked about AX equal to B, solution of algebraic equation. So something related to the matrix analysis and algebraic equation will be second part of this. So the problem 1 will be based on my notes that I sent you before. Then we go to problem number 2. Problem 2 is really related to modeling. Well, I mentioned yesterday about the mathematical concept. Maybe either problem 2 or problem 3 can be reversed in some sense. One, in problem number 2, if I want to continue the problem of mathematical background, I talk about eigenvalue, eigenvector problem. You solve some problems to obtain from a matrix how to obtain the eigenvalues and eigenvectors. So that is one part of the problem. The other one is related to Cayley-Hamilton. This would be something related to that homework that you solved about the mathematical background. I think it was chapter 3. Then we go to chapter 2, chapter 2 about modeling. Here, the modeling that I just described in the notes that I showed you a few minutes ago, the modeling, you have to know the both transfer function modeling and state space modeling. Maybe I give you one problem of modeling that a simple electrical circuit is given to you, and then I ask you to find transfer function, a state space representation, something like that as model of that. The second part of it, I give you the model, and I ask you to find, for example, from state space to transfer function, or maybe transfer function to state space realization, something like that. So that becomes problem number 3, and problem number 4 consists of also 2 parts. One is the response analysis for linear time invariant and response analysis for linear time variant. So exactly the sequence of material that I just covered for you in my summary notes. Now, after actually I'm done now. I'm open for any question that you might have, and you can share it with me. I can answer that. Go ahead, please. Any question? Everything clear, everybody?
Hi, Professor. Thanks for going over that. I have a quick question on calculating e to the AT. Is the easiest way to do that using Cayley-Hamilton or the Laplace method?
It is a matter of convenience. If you're comfortable in transformation of Laplace back and forth and the properties of Laplace transform, just use Laplace. Okay. If you're if it is convenient for you to do the Cayley-Hamilton, use Cayley-Hamilton. The 2 methods has this computational part that you should know. If you have e to the power AT computed based on, I just give you why, the computational task. When you have e to the power AT obtained with the inverse Laplace transform of SI minus A inverse, obviously you need to do the calculation of this expression, take the inverse of it, and then you do the partial fraction expansion, sort of, and then find out e to the power AT by inverse Laplace transform. However, if you go and write e to the power AT as f of A, and write it as the alpha 0I plus alpha n minus 1, a to the power n minus 1. When you write this one and you try to find this, you need to find the eigenvalues of the matrix A. So the determinant of lambda I minus A should be computed, find the eigenvalues. Once you find the eigenvalues, then you solve a set of algebraic equations, right? So here it requires eigenvalue calculations. You don't need to calculate eigenvectors, just the eigenvalues. And corresponding to each eigenvalues, you go and find f of lambda I equal to g of lambda I, as you remember. Solve the equations for alpha 0 to alpha n minus 1, and then you go back and define this f of n. Is that answering your question, Julia?
Yes, that makes it clear. Thank you.
It's really up to you which one you want to use. If you're more convenient, it's more convenient for you to apply the inverse Laplace transform and calculate this expression. That maybe takes a little bit more time for you to do the partial fraction expansion of each term. Here, the computation of eigenvalues takes your time, and then after that, algebraic equation should be solved, whatever you like. So that is the answer to the question. Any other question?
Hi, Professor. I have 2 questions. One is more just about taking the exam. I don't know if this was if you mentioned this earlier, but will we be allowed to use like a calculator to do some of the basic, like, will we have to do an inverse matrix for a 4x4 by hand or
Oh, no. I believe me, I'm not gonna give you a 4x4 matrix to take the inverse of that or anything like that. No.
Okay.
So there is no need for calculator, believe me.
Okay, that's good to
If
know.
there is an inverse calculation, it's going to be maybe 2x2. Okay.
Okay.
If I
And
give you something that it needs a little bit more computation and so forth, just leave it there and say that, you know, if the result is correct and you do only the computation, just say that, please, professor, calculate this for me.
okay. And then the other question I had, so so on the topic of eigenvalues and eigenvectors, so for an n by n matrix with independent, you know, n independent eigenvalues, that is pretty clear to me. What I'm not understanding is the whole you know, algebraic and geometric multiplicity when you have repeated eigenvalues, and like the generalized eigenvectors and how to find those, Jordan form, that sort of thing. I'm not able to understand that.
Yeah, as I mentioned to you, in order to find, the question is this: if when you have distinct eigenvalues, when A has distinct eigenvalues, lambda 1, lambda 2, and so forth, then if these are distinct eigenvalues, you can find for each one of them the eigenvectors. So you don't have any trouble to find this, because once you have the, let's say the eigenvalues lambda 1, you want to find V1. So you know that A minus lambda 1 times I times V1 is equal to 0. Do you remember that? You did the homework?
Yeah, yeah.
Okay.
Yep.
So when you have this kind of situation for each one of them, you will see that the rank of this matrix, when you substitute lambda 1 here, the rank of this matrix will be in such a way that you can only find only one linearly independent eigenvectors. Okay, so the rank of the matrix you can obtain. The nullity of that one dictates how many linearly independent vector solution you can find, and that will give you only one vector. Is that clear?
Yeah, yes. So that part,
you can find V1, V2, V3, and Vn, and then you can find the Q matrix, and then you can find. Now, when you have repeated eigenvalues, then we talked about the so-called generalized eigenvector. Okay? The generalized eigenvector is in such a way that, to make it very simple, is that you increase, well, let's say this lambda 1 is repeated, just assume, I don't want to write again. So if this one is giving a rank that does not generate enough linearly independent eigenvectors for these repeated eigenvalues, let's say you have lambda 1, 2 eigenvalues that are repeated. So when you calculate the A minus lambda 1I times V1 equal to 0, you will see that this, based on that, you can perhaps find only nullity becomes equal, rank becomes something, and nullity becomes 1. That means you can find only one linearly independent vector solution. So you pick that V1 for one of those lambda 1s. You can do that. But then at this point, if you put the lambda 1 again in this equation, then V1 becomes, you know, linearly dependent of that. So you cannot have two eigenvectors linearly dependent, because otherwise, if they are dependent, then you cannot take the inverse of that one, because the matrix becomes singular. Therefore, they bring this concept of generalized eigenvector. In that case, you increase this one to the power 2, increase that to the power 3, and so forth, until you can find enough linearly independent eigenvectors, and then you can stop. Let's, for the sake of manipulation, if you increase that A1 minus lambda 1I to the power 2, V, that becomes equal to 0, but A minus lambda 1I times V is different than 0. That becomes a qualified eigenvector. I already explained that in my lectures. If you go back and take a look again with the example that I gave, you will see that based on that, you can find generalized eigenvector, and then once you find that V that makes this one to be different than 0, and then V equal to 0 is based on this, you can find the eigenvectors. And also, one of them gives you one of the eigenvector with respect to one lambda 1, the other one with respect to lambda 1 again. Does it make sense?
I see. Okay. Yep. Yep. I think that makes sense now.
I
Yeah.
think if you did you take a look at the solution of the homework that I gave you for several matrices, how they to obtain the generalized eigenvector. If you go there, you will see that there was one, I remember vaguely, one of them was in such a way that you had to increase the power until it became 0.000000000. In that case, you see that you have a choice to find the generalized eigenvector that satisfies this, but the a minus lambda I to the power 2 different than 0 and so on. Is that understood?
Yeah. Yeah.
Yeah, go to the take a look at those examples and generate. Don't look at the example, but put the solution on the side and then try to derive it yourself, and then go back again and take a look and see how the steps are. That is the best way. If you look at my solution completely immediately, may not help you that much. So it is better that you do it yourself so that you get self-confidence. I hope that I answered your question.
That does. Yeah.
Yeah, just take a look at those examples. So any other questions that you might have?
Hi, Professor. I have a
Yes.
question regarding like
Hi,
obtaining
Professor.
Oh, sorry.
Oh,
Go ahead.
go
I
ahead.
have a question in homework 3, question for 4.16. So the question is to find the fundamental matrix and the state transition matrix. But if we use the Cayley-Hamilton method, then we get just the straight
Can you let me just put
transition
this one?
matrix,
Can you
right?
show me that, because I don't have access right now? So let me just see whether I can put you. Can you show your? Let me see whether I can put this one sharing. Oh no, not sharing.
Should I share my screen?
Yeah, hold on a sec. Let me see. I think
It says host disabled participant screen.
yeah, I'm trying to find out that participation. Doesn't give me the option for everybody. What can I do? It doesn't give me the option to give you. What is that?
So usually it's an option in the meeting settings, but I don't see your screen right now, so I don't know how to guide you.
No, I know, but let me see. Oh yeah, here, I found it. All participants. Okay, can you share now? I think.
It's still showing me the same error.
I just let it be all participant and start sharing with someone else. Let's see whether I put those, both of them. Is it possible now? Yes or no?
Yes.
Okay. Christina, show me. Okay.
So in this question, find fundamental matrix and state transition matrix.
Right.
So in the solution you've provided,
Yes.
this is using Cayley-Hamilton, it's directly finding the state transition matrix, right?
That's correct. Yeah.
So if we want to find the fundamental matrix, we have to use the long method, all of this.
If I give you a problem, this would be the most general solution. The second one with the Cayley-Hamilton is assuming that the commutative property is satisfied, alternative method. So for this example, it turns out that the commutative property, remember this integral times a
Yeah.
equal to a times the integral. If that satisfies, then you can use this alternative method. In general, alternative method works only when that commutative property is satisfied. The one that you showed, Christina, the one that you showed me up there, you know, go up a little bit. Yeah, this the process of finding a fundamental. Go to the previous page. Right. This method is more general.
Okay.
Is more general. But if I give a problem, I do not want to bother you. I give an example. If I give an example, I give an example that you can use either method, so you don't have to worry too much about proving the commutative property. Is that fair?
Yes, Professor. Okay.
Yeah,
Okay, thank you.
you're welcome. So any
Hi,
other
Professor.
question?
I also have a question regarding the transition matrix in linear time varying system. So, as we are obtaining the transition matrix, we first need to write the like x1 dot equals sum x1 plus x2, and x2 dot equals sum x1 plus x2, right?
Right. I showed you in my summary notes.
And when should we substitute like x1 0 into x1t? Like when should we substitute x1t to x1 0?
So I showed you here. Let me just go back then on the notes that I gave you.
Yeah, sorry, I'm just not clear. Like when should I do the substitution?
It's very simple. I'll tell you right now. So let me see whether I can show you here. Again, let me just go back to my. Oh. Can you see that? Hello?
No, there's nothing.
What do you mean there's nothing? Let me just then do you see my face?
Yeah, I can only see
Yeah.
your.
Okay. Okay, let's do this. Since I made yourself to share, can you show this page that I gave you or no? You cannot show this? Let me see. Hold on. Let me just see. I have to go to this page. I see it here myself, but let me see. Can you see now?
Yes.
Yes?
Yes.
Okay. So look, it's very simple. The first equation, x1 dot is equal to 0. You find x1 of t. Forget about the one that I crossed because I put for you 0. You have option to use t0 or 0. Okay? That is not important. Let us put the one with the t0 that you see. Okay, so x1 dot is equal to 0. So x1 of t becomes a constant. So if you put t0, then x1 of t becomes x1 of t0. This is the solution of this equation. Is that clear?
So this means that x1 t0 is k1?
Yes. But
Okay.
the k1, when you put t equal to 0, that becomes x1 of 0 or x1 of t0. Look, if you put x1 of t0 here, right, that becomes k1. So this is k1.
Oh, yeah, I got it.
So x1 of, then you substitute this one into this equation, you find x2 of t. The same way you put t equal to 0, you find k2, and you substitute back here, so you get this equation. Okay?
Okay.
This part, you find this, and you find this. At this point, you assume this initial condition that you see x1 t0, x2 of 0, these are not really the initial condition of the system that it's given. They are given at the beginning of the problem. Okay, so This is something that is given here, but we are not using this. It could be x of t0 equal 1, 1. But here, you are using x1 of t0 and x2 of t0 fictitiously to generate fundamental matrices. Is that clear? So how do we do that? You find two vectors that are linearly independent. If I put x1 of t0 equal 1, x2 of t0 equal to 0, and another one, x1 of t0 equal to 0, x2 of t0 equal to 1, this vector and this vector are two linearly independent vectors generating this and this. You substitute these two into this equation and this equation to find psi1 and psi2. Is that clear?
Oh, yes. Yes,
Yeah.
it's clear. Thank you.
So you put this again. Now you have an option instead of this 1, 0, 0, 1, you can put 1, 0, 1, and 2. You could put 2, 1, 0, 1. As long as they are linearly independent, they give you two vector solution based on these two equations. Okay?
Yep.
Very
Yes,
good.
thank you.
Very good. So I am in the process of going to a funeral, actually. So sorry about that. I didn't know, but my wife told me that there is somebody that passed away today. I have to go to the funeral. So is there any other question? I think you're all set, right, everybody?
Hi, any other questions, we can email them to you over the weekend.
If it is quick, just go ahead. Don't bother to send emails.
I was just wondering if you could provide an example of finding e to the exponential of at using Jordan block, but maybe that's better in an email.
Why do you want to do the Jordan block? It will power it. Why do you do that, Kevin? Why do you want to do that? Hello? Kevin, I lost you.
Hello?
Hello, yes, Kevin.
Yeah, I'm recalling a moment where you told us 3 different methods of solving the exponential was Laplace, Cayley-Hamilton, and using the Q inverse times AQ.
Yeah. So those are the best methods. Why do you want to go to the Jordan form and so forth?
I was more curious just how I would use the third method, because I don't think I've had any. I don't think the homework had an example of that.
Yeah, because the general solution is given to you with the formula in the textbook. If you have, remember that if you have repeated eigenvalues, then you have t squared, t cubed, the factorial, and so forth. There is a formula in your textbook that gives you how to obtain, how to obtain the Jordan form, right?
Yeah.
So when you have the Jordan form, let's say if you have two eigenvalues, -1, -1, one of them gives you e to the power minus t, the other one is t times e to the power minus t. There is a general formula in terms of the factorial in your textbook. If you have the Jordan form, let's say 3 by 3, then it's going to be e to the power minus t, all the diagonal e to the power minus t. The off-diagonal element becomes t times e to the power minus t squared over 2 factorial e to the power minus 2t. So the formula already derived for you in the textbook.
Okay.
Do you understand what I'm saying? I can
Yeah.
tell you, if you don't have to do that yourself anymore, because once and for all, somebody already did that for you.
I'll check the textbook, and if I'm still confused about it, I'll
just call me sometime or send me an email. I'll tell you.
Okay. All right. Thank you.
You're welcome. But I suggest that don't do that. because you might get into difficulty not to be able to put it in the right place, the right expression. Anyway, just use, my suggestion is that use the inverse Laplace transform or as Julia mentioned before.
Yeah, I've usually found those to be simpler too. So I'll keep that in mind.
Yeah, keep in mind to see whether it is necessary or not. Then you can send me an email. There is a formula that it's already derived when you have a Jordan block, how to find e to the power a hat t. Once you have e to the power a hat t, then you can find e to the power a t by inverse calculation. It's very time consuming that way. Okay, so I hope that I answered all the questions. Good luck to you guys. I'm gonna send you another announcement to tell you that the exam is closed, book closed notes, and everybody should come to the class hopefully on Tuesday. That is, at least I can see some of you that are in the companies working on that day. Please come to the class and take the exam. Thank you.
Thank you, Professor.
Thank you. Thank you very much.
Everyone. Thank you very much. Bye-bye.